Well, as Suhail said, so I'm going to present this new concept, and I have to say this is a team effort between Johns Hopkins University, myself, and Bruce Marsh, who is in the audience, then Pete Geiser from Global Geophysical Services, who provides expertise in fracture imaging and also in geothermal modeling. Then there's Peter Malin, who provides input on heterogeneity modeling. And finally, we also have a team member from ATK. They literally use rocket science in order to crack rock in the subsurface. And how do I advance the slide? So we are all aware of the fact that the heat stored in the Earth provides a gigantic energy resource. So it's only very hard to access this resource. So theoretically, the recoverable geothermal energy should be enough to provide energy for the United States for the next 2,000 years. So nonetheless, geothermal energy provides only 1%, supplies only 1% of the energy demand in the United States. Let's take a look at where the geothermal energy is stored in the United States. So most of the geothermal energy is present in basement rock, and then there are also sizable proportions in volcanic rock and in sedimentary aquifers. And actually there is only a small portion available in natural hydrothermal systems. So it turns out that most of the geothermal energy supplied in the United States actually comes from the hydrothermal systems, from the geysers in California. And so you can ask, why is this the case? So, well, there is a geothermal problem. So most enhanced geothermal systems target basement and volcanic rock. So these rocks are very difficult to image, and it is also very difficult to enhance the permeability of these rocks in a predictive manner. So very often hydraulic fracturing is used, and hydraulic fracturing does not uniformly fracture the rock, and so you might not be able to engineer permeability as you wish to do. And then finally, if you're working with actually hot dry rock, where hot dry rock does not necessarily need to be dry, but if it is dry, there might even be a problem of establishing a hydraulic connection between the injection and the withdrawal valve. And so a lot of money has been spent in order to make EGS, enhanced geothermal systems, work in basement volcanic rock formations, but to date it has not been possible to extract very large amounts of geothermal energy from these basement volcanic rock formations. So I'm not saying that it's impossible, and there are also examples of smaller plants that operate, but large plants, so we have not been successful so far. And so this is the reason why we are proposing a new concept for extracting geothermal energy from the ground. So we believe, as the previous speakers, that at this point it might be better to target hot sedimentary aquifers instead of basement and volcanic rock. And the reason for that is we can simply see what's going on in the deep subsurface with appropriate imaging technology. So what we are proposing to do is to build an enhanced geothermal system that mimics a natural hydrothermal system. So that means we are injecting cold water from the bottom and we are withdrawing it from the top. And in order to solve the permeability problem, we will create a vertical rubblized zone. So that's this orange plane here, which will mimic the heat exchanger of a car. So this zone here is rather large. So it's, for example, a couple of 100 meters high, a couple of 100 meters in the horizontal direction, and it is maybe 10 meters thick, and by that we have a large interfacial area, and that would ensure a high heat transfer coefficient. And what's also important in our new concept, we are aware of the fact that the ambient stress field in the rock determines the formation of fractures And so what we want to do is we want to build this radiator system in the deep subsurface where the principal stress is vertical. So that means the fractures that will be induced are also vertically oriented. And we also are aware of the fact that there is a direction in which the horizontal stress is maximum, and the injection and withdrawal wells will therefore be aligned with SHmax, the maximum horizontal stress. So how are we going to do this? As I said, we want to restrict ourselves for the moment to hot sedimentary aquifers, and the reason for that is there is imaging technology that can image fractures in these rock formations. So the imaging technology that we use is called Tomographic Fracture Imaging, TFI. And then we will also use rocket propellants in order to create the fracture system. So let me show you some slides about what TFI, Tomographic Fracture Imaging, is able to do. So Tomographic Fracture Imaging is able to image both natural fracture systems and also induced fracture systems. And they can be induced, for example, by hydraulic fracturing or also by propellant stimulation. So what we have here is so that's a real image from a site where we have here lateral wells, and so the brownish clouds here depict the fractures that have been induced by hydraulic fracturing. So this method is almost a real-time method. So in this example, in the Marcellus Shale, TFI has been used in order to monitor the progress of hydraulic fracturing. So what we see here is a horizontal cross-section through the deep subsurface. So we have here a lateral, and we have here a monitoring well. And at the beginning of the fracturing operation, you see here how the samplance increases with time and is propagating toward this monitoring well. And eventually the monitoring well is hit, and then there's here a period of silence where the pressurization is stopped and some background activity. So, and if you apply proper analysis, if you analyze the samplance data, so then you can actually image here the induced fracture. And in this instance, actually, the fracture extended into the monitoring well. So that was also verified independently. So that's one of the components of the new concept that we propose. The next component is to use rocket propellant in order to crack rock in the deep subsurface. So this technology has already been partially verified. For example, what we see here is the application of rocket propellant in an abandoned oil reservoir in Ukraine, and after they stuck the rocket propellant into the subsurface, so the well didn't produce oil for more than a decade, so the oil then started coming out. So we are proposing to use PEPS, Propellant Enhanced Permeability Stimulation, in order to build these radiator vanes. That's the heat exchanger that we want to build. So we will start out at the bottom, drill vertically down, and then drill a lateral, and use PEPS to frack the subsurface. At the same time, we can use TFI in order to monitor the effectiveness of the fracking operation, and that allows us to appropriate to place the next lateral. That's a stimulation well that is only used in order to insert the propellant, and then we will create more permeability around the stimulation well, and then we work our way up to the top of the radiator. So the advantage of PEPS is that you can directionally stimulate the rock, so it fires into a certain direction. It's not an explosion. So these are more or less continuous pressure pulses that are emitted for extended periods of times. So And the pressure pulses, they are so strong that not only that you can actually create new fractures in the subsurface, and that you are not only enlarging pre-existing fractures in the subsurface, which might then not provide the desired hydraulic connectivity between the injection and the withdrawal wells. So we have performed some tentative mathematical modeling on the system. Here again is our EGS radiator EGS. So we assume we can also look at the race of these radiator vanes, and if we do so, so here we have one vane and another vane, then we need to just simulate 1/4 of the system. So in this tentative simulation, we assume that the surrounding rock is impermeable, so that means there's only thermal conduction available for heat transport, and then these are the equations. And in the simulations, what we have been able to show that with this concept, you are able to withdraw geothermal energy in a sustainable manner from the deep subsurface. So these are some of the simulation parameters. So the vane in this instance is rather large. So this is not what we are planning in a prototype, but it's 1 kilometer high, and the laterals are 1 kilometer long. And in this simulation, we still approximate the vane, which is actually a rubblized zone of rock that is 10 meters wide. We approximate it by a fracture with an aperture of 1 centimeter. So this should give a conservative estimate of what's going to happen in a real RAD-EGS system. And that shows you here the simulation of this RAD-EGS system. So we have here the injection well, it's a 2-dimensional simulation, here the withdrawal well, and then let me just switch it on. I need my cursor back. And what you will see is actually that the ISO lines, if you take here a look of the ISO temperature lines, they are actually bowing upward, and that indicates that the cold water that you are injecting here, as it rises, it will actually heat up the rock, and that's due to the fact that the simulation also accounts for the geothermal gradient, which we assume to be 56 degrees Celsius in this example. So that mimics some field site that we have in mind. And from the simulation, you can then predict the effluent temperature, so that's the magenta color here. And again, you see here that the temperature of the produced water initially increases in a sustainable manner. So that means you are not losing efficiency during the operation of the plant. And also you can determine or estimate the amount of electric energy produced here, where we assume the Carnot efficiency of 100%. So that's an overestimate. So yeah, we need to go to the next slide somehow. Next slide. So that's just if the movie doesn't work. So we are also trying to, develop analytical models in order to design Radiator EGS. So one quantity of interest is the travel time of the cooling front as you are injecting cold water. Well, a cooling front will propagate from the injection well to the withdrawal well, and you can use relatively simple dimensional considerations in order to calculate this travel time TC3, the vertical travel time. So basically, you are balancing the geothermal energy that you are withdrawing laterally from the rock formation with the geothermal energy produced at the withdrawal well. And then you can solve here for TC3, so that's the travel time of the cooling front, and you obtain this expression. If you plug in the numbers for the parameters that I've chosen, the travel time is about 10 years, and that corresponds roughly with the time when the maximum effluent temperature occurs here. So what we need to do in the future is also account for the geothermal background gradient, how this travel time depends or varies with this background gradient. And what also needs to be done is we also need to account for natural background flow that will occur in a hot sedimentary aquifer. So there are also quite significant background flow velocities in the very deep subsurface, and they will also replenish a geothermal system and increase the lifetime of a geothermal reservoir. So we have partially begun working on these efforts. So there have been simulations performed where we replaced this 1 centimeter fracture by a rubblized zone of thickness of 10 centimeters. And as expected, the simulations indicate that the lifetime of a geothermal reservoir of the RAD-EGS system will increase. And if we finally will also account for the natural background flow, the lifetime will even further increase. And that brings me, I think, to the last slide. So what we are proposing to do is we want to use state-of-the-art permeability enhancement methods together with imaging to construct the equivalent of a radiator in an internal combustion engine. So this is here the sketch, and it's possible to do because we use fracture imaging. So we can construct this radiator by first with drilling vertically down, and then we drill a horizontal well, and we create directional permeability by firing rocket propellant. Then at the same time we use TFI to identify the stimulated zones, and by that we can place the next stimulation well appropriately, enhance permeability again, and we work our way up, and by that we should be able to create this large rubblized zone in the deep subsurface. So the numerical simulations confirm that this geothermal energy is extracted in a sustainable manner from the deep subsurface, so the effluent temperature actually even increases due to the background geothermal gradient. So we are kind of emulating a hydrothermal system, and in addition we have also buoyancy effects which decrease the amount of pressure needed to drive the system. That's like in the previous talk with the CO2. So there's more work to do. The models that we have developed so far, analytical and numerical modeling approaches, they need to account for background flow and also put heterogeneity in the subsurface. So we kind of expect that the heterogeneity in the radiator veins is not so important, because we really expect that we are creating a rubblized zone that, again, mimics the heat exchanger in a car. However, if we are going into the surrounding rock, heterogeneity will be very important. And then finally, so there is also financial modeling going on by Jim Geiser, and that indicates that the Radiator EGS system can be economically feasible. So we are optimistic about this effort, and there are indeed plans underway to build an actual Radiator EGS system in the deep subsurface. And with that, thank you for your attention, and I would be happy to take questions.
Any questions, please?
Yes, please.
One comment and a question. First of all, I think it's an intriguing concept.
Thank you.
Please don't base your financial modeling on 100% carnot efficiency.
Yes. I don't think we do that. I just did it for this graph. And maybe what I should also add, I think for me personally, it's very difficult to quantify the economic benefit if you compare that to burning oil and gas. I think we all know oil and gas is very inexpensive right now, but actually what also needs to go into the calculation is the environmental impact, the carbon footprint, and there I think geothermal energy will always be ahead. But
Please.
Yeah, I mean, the energy output, I think, was thermal energy, right?
no, It was actually electric energy.
Okay, because that's roughly 10% of the problem.
Yeah.
But anyway, but my question was actually, so when you call a radiator, it sounds like, you know, you have conductive heat transfer to the surrounding, but you basically, with the rubblized zone, you're creating an effective heat transfer situation within that sheet, basically.
Mm-hmm.
But then you didn't have any background groundwater flow, so you basically still have pretty much conductive heat transfer to the surrounding. And then with future simulations, when you turn on
Yeah.
background heat,
Yeah.
groundwater flow, you get effective heat transfer to your zone,
Mhm.
and then heat exchange will be a lot more efficient.
Yeah. Yeah, I think largely you are correct. So the analogy between the car, the radiator in the car is in the car, you are injecting air, which you are heating up to cool the motor, and in our case, we are injecting cold water that is then heated up by the rock formation.
It's like it just does it. I mean, normally these heat exchangers that have been proposed in the past are obviously more linear features, right? Not a sheet like you proposed.
Yeah.
And the problem always has been that conductive heat transfer pretty much kills it very quickly
Mhm.
because you build this halo zone around this,
Mhm.
around the heat exchanger, and then you're done with the
Yeah.
conduction. But in your case, since you're making a very large surface to volume ratio kind
Yeah.
of system with the sheet, I think it
Yeah.
would actually work to have that almost conductive heat transfer from your
Mhm.
radiator, so to speak,
Yeah.
to the surrounding. It's very interesting.
Yeah, I think key is really to create kind of a large connected permeable zone, and then I think even the models that have the halo in them actually still provide significant amounts of geothermal energy. But if you do not have the connectivity, and that could be, for example, the case if hydraulic fracturing doesn't do what it's supposed to do, you're just not getting the heat out.
What is the environmental impact of using rocket fuel?
Sorry?
The environmental impact of using rocket fuel?
All what I have heard is I think there is very little environmental impact, so there are no large amounts of water needed, as in hydraulic fracturing. There are almost no chemicals injected into the ground. I think there's a small amount of gases released, so it's, I think, really nothing of a hydraulic fracturing operation. So personally, I think you should not be too concerned, but we have to look into the issue.
Any other question? I have one.
Yeah.
So when you create that sheet with the tabs, actually you end up by pretty much drilling an extra horizontal well. And
Yeah.
each one is very costly. So I was wondering what is the economical
Yeah.
feasibility of that, especially for geothermal industry.
Well-
It's too expensive.
Well,
versus
you are
oil.
correct about it. It is costly to drill laterals, but one thing that I should also have made the point that if you are drilling in a hot sedimentary aquifer, it's much less expensive than
Definitely,
drilling
yeah.
into basement rock.
Yeah.
So it might work out.
Yeah, for sedimentary basin, I understand. And then for the second, maybe it's a comment, it's rather than having two wells that come from each, you can use one coaxial well for the extraction and the injection. So it's a single well, but it has coaxial well, they call them. So you can, so to save more money
Yeah.
on drilling from the other side.
I'm not sure whether I completely understand, but I think one important factor, we can talk afterwards about this,
Yeah,
is
of course.
we need to work with the ambient stress field.
Yeah,
And
yeah.
the ambient stress field will create vertical fractures when stimulated that are directed
what I'm
in a
trying
certain
to say, rather
direction.
than having a well comes this way and the other one comes this way, so to save some of the drilling here, you can have a well that they are the same configuration, but you use the same vertical well to drill the two horizontal wells. So they call them coaxial wells.
Okay.
Well, thank you very much.
Thank you very much.
All right,
Yeah,
thank you.
I will think about.
Or-
I think your suggestion is
We'll
very good.
talk again, all right.
Yep.
We'll move to our next speaker, which is Lawrence Hutchison from Lawrence Berkeley Lab.